All right, what are we talking about?
I just kind of need like a place to start.
Okay, so let me draw something out. So for number two, you've got some situation like this, I believe. I think it's MOSFETs. And this should be PMOS current mirror up top, if memory serves me correctly. And there's our output voltage. So let's call this M1, M2. I think this is MREF. This is IREF. Here's VN. And I tell you some very strong hints, at least I felt they were very strong, that AV could be expressed as negative GM R out, and that GM could be twice ID over VGS minus VTH, I believe. That, okay. So what is the short circuit transconductance of this going to be? Positive GM1, right? So just to be clear, we'd really only need to be looking at, like, we would short this guy out, right? Which is going to make any resistance looking up not matter.
Is that because it's around the
Mhm. So from a small signal perspective, everything between this node and this node is grounded out. Yeah. So you would just be looking into the drain terminal and trying to find the transconductance for literally just a transistor, which is just going to be its transconductance. So GM capital should be GM1. Okay. What should R out be for this thing? Why is it taking you so long? R01 in parallel with R02. Right? So R01 in parallel with R02 is 1 over lambda n ID1 in parallel with 1 over lambda p ID2, right? So we can make this do some things, okay? So I'm going to multiply those together. So that's going to look like 1 over lambda n ID1, lambda p ID2, all divided by 1 over lambda n ID1. I'm giving myself space there. 1 over lambda p ID2. Okay with that? Now I'm going to multiply this guy by lambda p ID2 over lambda p ID2, and this guy over here by lambda n ID1 over lambda n ID1. So I wind up having a common denominator of lambda n ID1, lambda p ID2 through everything. And so all that shakes out to be is 1 over lambda p ID2, excuse me, plus lambda n ID1. What can I say about the currents flowing through the drains of M1 and M2? They're the same thing. So those are just going to look like IDs. And so I wind up having 1 over ID times lambda n plus lambda p. What happens when I apply this gain relationship where GM is equal to this thing, right? The IDs cancel. So I'm going to have AV is let's see, twice ID over VGS minus VTH times lambda n plus lambda p times ID. And this should allow me to calculate VGS by rearranging it. And then once I have VGS, this problem gets way, way easier. So that's as far as I'm going to go, because I just worked half the problem, if not more.
On that VTH, that's VTH.
So it would be N because we are using the transconductance of transistor M1, which is an NMOS transistor. Mhm. Yep.
I know North was gonna talk to me about it, because what's your office hours? Can you talk more about the 4 or 5, anything's on the line of symmetry, kind of what that?
Sure. So for homework 5, particularly calculating your differential mode gains. So you guys had I'm just going to put these as resistors for now because I don't really care what they actually are. It's all looks like a resistor to me. So this is our normal differential pair. I'm going to be lazy and not label a whole hell of a lot of things here, right? And when we looked at our small signal analysis, this node X was equal to 0, right? So in homework set number 5, I gave you guys circuits that looked very similar. But instead of putting just a current source there, effectively what I put is a small signal resistance. Okay, so that current source connected transistor is playing the role of, or the transistor down here is playing the role of a current source in a large signal configuration and just the resistor in the small signal configuration. The circuit is symmetrical, so that voltage there is still literally going to be equal to 0. So it's not going to impact your differential mode gain literally at all. This resistance right here, which would just be R0, whatever the hell the label of that transistor is only going to show up when you're doing your common mode gain calculations because those depend on the tail resistance. That's literally it.
So that node 0 if your top two resistors aren't the same.
So when we have a small amount of asymmetry, it's not going to be exactly 0, but it's going to be close to 0. Only, yeah, so just treat it like it's 0. So only if there's a large mismatch should we see that that voltage shifts significantly away from 0. What I was mentioning to North when he came by in the office hours was effectively, literally, anything that lies on that axis of symmetry from a small signal perspective is going to look like 0. So like in some textbooks, and this is literally just an exercise in making shit annoying to make you guys analyze things. You'll see stuff like they'll put a resistor across this guy and then take the output voltage to be here. So you could literally just split that resistor up into two different parts along the axis of symmetry in order to analyze the circuit using the half circuit method and all of that kind of stuff. That is just esoteric garbage. No one ever actually does that, which is why I don't bother showing it. Yes.
Real quick on that. If it's not for the fact, if we're allowed to assume just like a one-sided answer.
Yeah.
Do all of that.
100%. So yeah, so you can do a formal derivation like we did in class introducing things. So you can analyze the left-hand side, analyze the right-hand side where, you know, we apply 1/2 of the differential input voltage on one side and negative 1/2 of the differential input voltage on the other side. Or you can apply all of the differential input voltage on one side and none of it on the other side. And you find out that the gain of the half circuit is literally the full gain of the system. Doesn't matter what percentage of the differential input you put on one side or the other, the gain is going to be the exact same thing as the half circuit.
Oh, I already kind of homework it for, but the last problem where we two cascades, we were allowed to assume they were matching.
Absolutely, yes. So for that particular problem, what I was expecting you guys to do was effectively say, circuit symmetrical, so we're going to use the half circuit method, draw the half circuit, say, oh, I'll be damned, this looks like a cascode amplifier loaded with a cascode current source, which looks like this, and call it a day, or which has this relationship. Yeah. So I saw a couple of students came by asking questions about it, and I saw that they had derived everything. Nothing wrong with that. I did not need you to do that. Literally, my goal at this point, or your goal at this point should be, I know what that looks like, and then write shit down. Yes. So going back to problem 2, let's scroll back up here, right? So I walked you guys through solving for VGS, right? So once you know what VGS is, then you can solve for the drain current ID flowing through transistor M1, right? Because it's just 1/2 mu n C ox W over L, VGS minus VTH. So you can solve for that ID. The current that's flowing through transistor M1 is literally the exact same thing as the current that's flowing through transistor M2, right? Because they're connected effectively in series. We don't have to worry about base currents or anything like that because they're not BJT. So if we know the current flowing down through transistors M1 and M2, and we know our supply voltage, we know how much power is consumed by the right-hand half of the circuit, which tells us how much power is left over for the left-hand half of the circuit. And that lets us know what IREF has to be. Once we know what IREF is, we can compare IREF to ID1, and now we know how our current mirror has to work in order to multiply the current to get the right drain current on the right-hand side. So now I've told you how to do the whole problem.
We'll get answers for 5.
Yes, for sure. Gonna work on that. I've got a meeting immediately after this class, and then I've got to think about 2 hours to work on that, and then meetings for the rest of the afternoon, and then tomorrow I'm going to lock myself in my office and tell everybody to piss off so I can finish making my notes for Friday. Pardon? My outfit looks great, thank you. I really like these shoes for what it's worth. Yeah. on a completely unrelated topic to electronics, I don't know if you guys get emails from Converse constantly, but I do. Surprise, surprise, right? They have a new like Dungeons and Dragons collection for any of you nerds that want like dope ass shoes with dragons and all kinds of stuff over them. I have not yet ordered a pair, but I will be. Getting your credit card out now?
I mean, I just Googled Converse D&D collection.
I really like the green and black pair.
You're not for them? You're gonna get home blue?
No.
Are you talking about the the main color being green or the main color being black?
Main color being black and the accents are green.
I agree.
Yeah.
The-
I think it'll look real nice with my Misfits t-shirts, but anyway. Yes, Jake. Sure, go for it.
If I have a circuit.
Okay.
You have a voltage source
Mm-hmm.
that's hooked up in series with an inductor,
Mm-hmm.
capacitor, and then another inductor.
Mm-hmm.
And then after a while, you have a switch that turns on to cut the voltage source, destroy the voltage source basically. What happens to all of that? Does it just kind of?
So let me draw something here.
I was just like, what happens? Wait, this.
So you have some voltage source, and then you have an inductor, and then a capacitor, and then I think you said another inductor. And then I'm going to put a switch right here. You want to know what happens. So in an ideal case, you have created a magical energy storage tank that will never lose its energy. In a real case, we know that resistors and inductors, inductors and capacitors have a finite resistance associated with them. So it's just going to convert that energy into heat.
So it'll literally just, it's gonna be just a very bad battery.
Yeah, like a real terrible battery. Yes.
Okay. Trying to think of like point and do things.
Yeah. So like there are very large capacitors. So and I wasn't like, I was watching some YouTube videos about all these projects, and people making their own voltage regulators and all that kind of stuff. And they've been using these devices called supercapacitors, where effectively it's like 1 farad capacitors or larger that are very small, but the voltage rating on them is incredibly small. So like 2 to 2.5 volts or whatever. And so like one thing that you have to watch out for those is because they're so large, like they take a very long time to charge up. They also take a very long time to discharge. If you were to disconnect one and you don't allow that energy anywhere else to go, it will kind of stay there. And then when you touch it, it'll shock the hell out of you. So I don't think I've made any secret of the fact that like I love guitars and everything guitar related. When you're servicing a tube amplifier, you actually have to use a special set of tools that have a specific, like your screwdrivers have a wire that comes off of them to shunt things to ground, so that if you accidentally touch one of those capacitors, you don't kill yourself because of how much stored energy they have in them. So like if you fully charge a large value capacitor and then you disconnect it, it will hold on to energy because it has nowhere else to go until you give it something to discharge to. So you better be safe on what you're discharging it to.
That kind of answers the question.
Yeah.
More or less supposing with that thing.
Yeah. So yeah, you just have a very odd battery type thing. Yeah. So the capacitor would still probably have some energy stored, but the inductors I don't think would, because there's not going to be any magnetic field because there's not any way that current can flow. James, I sincerely doubt that. Yeah.
Put two voltage sources.
In reality. So it depends on what they are, but effectively, you're just gonna cause a lot of current to flow through whatever wire is connecting them, because they're gonna try to balance each other's voltage. So if you put, let's say that we have a 1.5 volt battery, like a AA battery or something, and it's at about 50% charge, and you put another AA battery in parallel with it, and it's at 100% charge, and you wire it up like this, the voltages are not exactly 1.5 volts. So a fully charged 1.5 volt battery actually probably has closer to 1.7, and an almost discharged 1.5 volt battery probably has somewhere closer to 1.4 volts. So there's going to be a potential difference that's going to cause current to flow through that wire. So what you're going to see is probably sparks and a whole lot of heat. So way back in the day, in the freshman series, like you guys had battery packs and all that kind of stuff, and I think it already had the barrel jack soldered onto it for you. When I was teaching the class, it did not. And so we had to warn the students constantly, don't leave batteries in your battery pack because those wires are loose and you can accidentally short it out. And so people would just not pay attention, throw it in their bag, and then open up their bag a couple of hours later and just find a big melted plastic mess. And it's because the batteries just heat up so much by trying to balance the charge across all of that, that just melts the plastic and then ruins their robotic kit. So you realistically, you need an integrated circuit called a charge controller to make sure it's done safely, because you can always overcharge and over discharge things. And anytime you're overcharging or over discharging, it's just heat. And if some battery cells, particularly lithium ion battery cells, get too hot, they tend to explode. And the problem with them exploding is that they have hydrofluoric acid in them, which is a hugely dangerous chemical, completely odorless, completely clear, so it just looks like water. However, 1% of your skin area covered by hydrofluoric acid should make you have a heart attack within an hour. What it does, what that chemical does, and I know a lot about this chemical and about how damn dangerous it is because it's used in a lot of fabrication processes for integrated circuits and stuff like that, so I had to use it in grad school. It effectively leaches the calcium from your bones and causes your blood to crystallize. It is terrible, terrible stuff.
Near that, I was gonna replace my phone battery, I was gonna wear gloves.
Yeah, and you need gloves. I'm trying to remember what the high density polyethylene, I believe, HDPE gloves and stuff like that. It won't heat through that. So like you usually have to store it in specialized containers specifically so that like it doesn't react strongly with like organic tissue or anything like that. Like I said, it just bleaches the calcium out of your bones and kills you. But it's also used to like very rapidly etch metal and glass and all of that kind of stuff. So it reacts extremely violently with something, and it doesn't look like it's doing anything for organic tissue. So you use like high density polyethylene because it's so incredibly inert that it doesn't really do anything to all of those hydrocarbons. Yep. There is an episode in, I think it's season 1 or season 2 of Breaking Bad, actually, where they try to use hydrofluoric acid to dissolve a body. And it wouldn't really do that to the body, but it definitely would eat its way through a bathtub, which is what it's.
Oh, yeah, went to the second floor.
Yeah. Yeah, an old cast iron tub, it would run roughshod over that pretty quickly. What's absolutely mind-blowing to me is like old school frosted glass was just literally untrained people using diluted hydrofluoric acid and literally just spraying it on windows and then wiping it off, and that's how it got that frosted look. So they were like inhaling it. It was crazy diluted, but still that just seems like wildly dangerous to me. Like anytime I've ever been near it when it's out, I'm in full PE, so like full gown, big chemical gloves, goggles and a face shield. I do not want that stuff ever touching me. It terrifies me. We have to keep, like when we're working in the IFM, we had to keep a tube of what's called calcium gluconate gel, which is just a really high calcium concentration gel, so that if it touched you, you just rub that all over where it touched you so that it would leach the calcium from that and not you while you were on your way to the emergency room. Very, very nasty stuff.
Just a general question. I don't know what y'all working on. I looked up solar panels last night, and how they work by dump the heat's knocking off, electrons make it go in. Why couldn't you heat a resistor hot, draw energy from it like that? Just generate power.
So typically when you heat up something, so like the filament of an incandescent bulb operates by what's called thermionic emission. And that is effectively you're heating up a material so hot that it's causing electrons to have enough energy to jump off and produce photons when they move to a different valence state and all of that kind of stuff. Solar cells work by some similar property where incoming light comes in and it is energetic enough to cause an electron to move from the valence band of your semiconductor material into your conduction band of your semiconductor material before it gradually finds its way back down. So it's just using photons, which is just electromagnetic waves, to cause charge separation in your device. So you're saying, why can't you just heat up a resistor and use it effectively?
Yeah.
You kind of can. Like anything that you can put heat into, you can get heat out of as energy. Energy in is equal to energy out. A resistor is just really bad at it because it's designed to just convert electrical energy into heat, not really the other way around. So resistors have their resistance because they are usually just some amorphous material with lots of places for electrons to bounce off of, right? So when we think of like really good conductors of electricity, like metals and stuff like that, they're typically crystals. And so an electron can travel a relatively large distance before it encounters a scattering event. So that's why electricity flows well and we have a low resistance. A resistor is designed with literally the opposite, where it's as much garbage in there as we can make it have, so that electrons are constantly scattering and converting electrical energy into heat. So it's going to be hard to put heat in and get electrical energy out because its job is literally to do the exact opposite. It wants electrical energy to go in and it converts it into heat. If you want heat transformed into usable energy, you want a thermoelectric generator, which is just the exact opposite of a Peltier cooler, right? So you're using, is that the CVAC effect, I think? So it's usually, I think it's like a P-type crystal and an N-type crystal. It's been so long since I took Sam's class on this. I think it's like a P-type crystal and then a metal and then an N-type crystal and then a metal and then a P-type crystal and then a metal and then an N-type crystal and a metal or something like that. So you're using thermal coefficients of the metal junctions and all of that kind of stuff so that effectively when you heat up one side of this thing and you keep the other side cool, the temperature gradient winds up inducing a voltage across the device. You should have learned about that in 334, I think. Yeah. So you thermoelectric generator is what you're specifically looking for if you're trying to harvest heat energy and convert it into electricity. The problem with those, and I say that from a senior design teacher who's had several groups try to use them, is that the temperature gradient needs to be very large in order to get any useful voltage out of it. And just because it can produce a good voltage doesn't mean it's particularly great at supplying current. So like I had a group of students that were trying to use an array of those thermoelectric generators to just recharge a battery to power like a vest that would have lights on it and stuff for construction workers to use in the evening. And when I made them do the math, they found out that with their array of thermoelectric generators and the expected temperature gradient of a person putting, one side of this on their skin and the other side out to exposed air, it would take roughly 21 years to charge the battery that they were looking at. They're quite inefficient for very low temperature gradients. Did I kind of sort of?
That was a question, that was interesting.
Yeah.
Actually, your design came in my head of why not do a solar panel that way, but my real question was, what would we consider? What's the deficit there?
So another group tried to use, so when solar panels are exposed to direct sunlight, they obviously die. Anything that's exposed to sunlight and stuff over time. So they were trying to use a thermoelectric generator setup in order to power a microcontroller and a few motors, so that effectively it would try to maximize the output of the solar panel. So they had a TEG trying to power a microcontroller and all of that kind of stuff to move the solar panel into a position where it would get the maximum exposure to sunlight. But once again, the output of the TEG is so small, would never actually cause the motor to do anything. Right? They couldn't even get it to like, get the microcontroller to recognize it was receiving power. They were using incredibly cheap, shitty ones, like stuff they found on Amazon for roughly, $10 to $12 per unit. There are more expensive ones, but they're still not that much more efficient, even though they're made much more exactly. So it has potential for application. You guys, you guys have had thermal, right? So you guys did the project. That little white block thing on your manifold? Oh, well, son of a bit. They would, in thermo in the last couple of years, they were actually using thermoelectric coolers or LTA coolers, which are literally just the exact same thing as the CEG for the thermo projects. But I guess they're not doing that with you guys anymore.
It must be like.
Mm-hmm.
They're not efficient. They're still like 50% terrible, but 50% efficient is not terrible.
Yeah, so 50% efficiency is I think the best that you could do an internal combustion engine is somewhere in the ballpark of 30 to 35%. Mhm.
They make a like use of the violent lightning around the regular lights actually where they switch solar panels.
Interesting.
But it's not as efficient.
Well, so the efficiency of solar panels, how efficient do you guys think a solar panel is? Yep, like 10 to 11%. Super, not particularly great. Dr. Zavanovich has been doing research over the last few years on effectively organic solar panels, which are even less efficient. However, the processing and all of that kind of stuff is not terribly harmful to the environment, and it doesn't require materials that are, sourced by forced labor. So there are arguments to be had about, less efficiency, but not killing people to make them.
You still doing it?
I have a research project with Entergy where I am evaluating their lightning protection standards to see if their current lightning protection equipment would be of any use in the event of a high altitude electromagnetic pulse. So that's my research project that's going on right now.
Other things, right?
So, I just kind of got handed that project. It was originally a buddy of mine's, who wants to go, he left Louisiana Tech to go work at a lab up at MIT. And because I was listed as a co-PI on there, because like it came to me first, and I was just like, I don't want to do this, they're willing to do it and whatever. And then, put my name on it, it'll make us both look good. And so I was effectively just supposed to be consulting on it. Well, when he left, it was just like, hey, it's yours now. So anyway, so, I'm saying that to say that I don't participate in a whole heck of a lot of research like that anymore. I'm trying to move more towards engineering, education, research, because that aligns with what my job responsibilities are more. But so like Dr. Wong, who you guys, I don't know if have had yet, he does a lot of research in, robotics and artificial intelligence. Dr. Chen, who you guys probably haven't yet had, most of his research is involved with communication systems, but also blockchain. Not sure how. That crypto doesn't make any sense to me, so I just think it's witchcraft. Dr. Zavanovich is usually involved in semiconductor research, particularly relating to optoelectronics. Dr. Batari is power systems research. So he's got a project with, I think he's got at least one project with Entergy, might be multiple, and he's also got a pretty large Board of Regents grant thing going on right now. Dr. Amir's background, I'm not sure what his graduate research looked like, but I know his post-grad research was actually in quantum computing. And he'll be teaching a class in quantum computing in the fall. And he's going to be doing a class in radio frequency electronics over the summer, I believe. I think that's all of our faculty. Oh, and we hopefully should be getting a new faculty member, Dr. Arwa Frywan. And she's going to be electrical engineering faculty, but her research is very highly aligned with biomedical engineering, but it would be like bioelectronics and stuff like that. So applying EE principles to biomedical engineering problems. So yeah, I mean, none of the electrical engineering classes are going to be related to an honors program thing or anything like that, unless you guys are just itching to do an honors contract or some such nonsense, which, you're welcome to do. I have it on my to-do list literally for this weekend, because you're not the first person to ask about it, to compile that list of classes that I intend to have offered for the entirety of the next academic year. So that would be this upcoming summer all the way through next spring, when most of you guys are expected to graduate. Hopefully all of you guys, but I will hedge my bets and say so for most of you guys. So I'm going to have that done this weekend, and then I want to say that the early advising period, I think it ends on May the 3rd, if I'm not mistaken, so the week before the Senior Design Expo. So I'll be doing advising the week leading up to Friday, May the 3rd, I believe. I might be able to start doing some of it towards the end of next week. It just depends on how much work I can get done on the notes for this class over, this weekend and all that kind of jazz, but yeah. So coming up soon, and I'll give you guys a big list of classes. I will also make sure to include which classes also have a co-listed graduate class for those of you that are interested in doing the concurrent enrollment program. And I'll probably talk a little bit about the concurrent enrollment program in 336 at some point next week, just so that, you know, I have the overall majority of you guys that are going into your senior year in this class. So I don't waste my time talking about it in, you know, dribs and drabs. I had all of you at the same time. Yep. Jake, what up?
So battery,
Okay.
that's a good way to put it. More specifically, like chemical batteries.
Mhm.
That we're working with. Do you think with like the rise of superconductors and such that will ever kind of be able to push over to storing energy in terms of electricity? Or to
I'm not entirely sure that I understand your question. So when I'm thinking about your question, what I immediately think about is some work that Nikola Tesla actually tried to do. I guess this would have been in the 1970s, I'm not sure, about like wireless transmission of energy over long distances, effectively having a grid without physical infrastructure. One of the largest problems with that is that hopefully you guys are all aware that electric fields roll off as a factor of R squared, and I think magnetic fields as R cubed. I might have those backwards, but effectively, the further away you get from the source, the lower the field strength is. So like storing energy in a field at a small scale thing is easy. That's literally what capacitors and inductors are. Large scale, it's harder to do because the further you get away from your source, the weaker the field is.
My question is more like supporting the current of like small scales, like for a small scale circuit to supply. Because I'm thinking of like, you know, your basic AA method.
Mhm.
Instead of that, in terms of its like chemical properties, like a battery like that, in terms of chemical, we have these kinds of batteries for the electric field.
Yeah, so you're literally describing a large capacitor.
Yeah.
And it already exists. Possibly. So the issue with like the supercapacitors and all of that kind of stuff is just thinking about things in the context of just a simple RC circuit and how long it would take you to fully charge one of those, right? So the larger the capacitor or the capacitance is, the longer it takes to charge and the longer it takes to discharge. So in the context of a voltage regulator, that's a very good thing. So meaning that if you have a simple electronics-based voltage regulator in parallel with a supercapacitor, it's going to make the output of that voltage regulator look like whatever voltage is stored in the supercapacitor, right? If your input voltage dips low, your supercapacitor will very, very gradually drain its energy away. And so the voltage regulator portion isn't really doing anything. Whereas when the input voltage is higher, it's trickle charging that supercapacitor while also boosting the level of the signal to whatever the Zener diode is telling it roughly should be. So in that application, like it's doing a really good thing. It's keeping, so voltage regulator output, we hopefully know, isn't exactly stable. It depends on the operating point of the diodes and all of that kind of stuff involved. The presence of the supercapacitor just makes that more stable, effectively eliminating ripple because we're putting a really big capacitor on there as effectively as filter.
My question is, right, so this is long, like, conversation I had about electrical cars. Like, electric cars and how the biggest thing is the fact that car battery is kind of hot. Chemical batteries are very low. I don't remember the exact context of what I was talking about.
So in the context of an electric vehicle or something like that, I think probably the most important part of that would be the energy density of whatever you're using to power everything. So meaning if you were able, and I don't know of anything like this, but if you were able to store a whole bunch of charge in a very, very small space or whatever, like so that you had a very large energy density, that would be good because it would lower weight and this, that, and the others. That being said, like one of the advantages of using those really big batteries is it provides a low center of gravity for the vehicle and rigidity. So like they're part of the mechanical structure, not just the electrical systems. So like you would have to redesign a whole lot of things to provide the mechanical rigidity that the batteries are currently used to do. So like if you made your car ultra lightweight, that's great and it'll go real fast, but it'll also flip over.
So it just becomes a problem purely out of the field and moves out more people.
Yes. Speaking of electric vehicles, how did you guys do at the EcoCon stuff? Okay.
Pretty good.
Yeah, so that's what I was, so that was with a fuel powered vehicle. So so that program still isn't quite doing an EV yet?
That's what I'm planning to do next year, that's concept, so working motor on the road. Before you do the school year, pretty tight deadline. Yeah. So,
Are you guys going to design your own electronic speed controller or?
that's fine. The other thing we have to kind of have a bunch of like.
And are you going to use a brushless DC motor or, okay. Outrunner or inline? So like an outrunner is, the outside is the rotor and the internal part is the stator.
Like the whole car is usually. Definitely.
Outrunner motors to me are really interesting because it actually reminds you, so an outrunner motor effectively works like it's a DC motor. And you've got all these different coils and you use MOSFET to effectively switch on different coils at different times. And it's producing a magnetic field that is attracting a permanent magnet that is connected to the rotor. And so it's just dragging those along in sequence. And so however fast you switch your MOSFETs on and off is however fast the motor spins. That is incredibly similar to these really interesting but completely useless electromechanical motors that people started making when MEMS got big. And so it's effectively a capacitively actuated motor to where you use parallel plate capacitance and turning capacitors on and off to drag a gear around its, I guess, cylindrical path or whatever. So it's completely the opposite. Yeah, so it's electrical field driven instead of magnetic field driven. They tried to use it for like some micro scale drills and all this kind of stuff, I think in dentistry, but I don't know if anything ever came out of it. But the exact electrical dual of that is the motor that's used in practically all drones and all that kind of stuff. I find it yeah. Cool.
They're not the same.
Why does it burn if too much current passes through it? That's the answer. To all of it.
Like a motor, like an electrical motor, electrical generator. Same thing, just live within your usage.
Yep. It is literally, so the difference between a synchronous machine and a synchronous motor, or excuse me, the synchronous generator and a synchronous motor is literally if you're using electrical energy to cause the rotor to move, or if you're moving the rotor with a mechanical force and generating electricity on the other side. It's literally the exact same machine.
It's so fascinating, because it's just like, it's just, you're able to move that energy between those two mediums, it doesn't need to. And it like.
Yep.
You need to find.
All because of magnetic fields.
Why do they? He's like, you tell me that like we don't live in a world full of like magic and stuff, and when you show me a magnet, you just tell me to believe that that's the thing that exists.
So the spin of an electron has an associated magnetic dipole moment, and the orbit of an electron also has an associated magnetic dipole moment, and so that's why magnets are things.
That's so weird. That's pretty powerful.
And depending on how the spin dipole moment and the orbital dipole moment line up is whether it's, you know, ferromagnetic or paramagnetic or diamagnetic and all that kind of stuff. Like, do they cancel each other? Do they add a little bit? Do they add significantly?
Right? What a pole is, and like what a dipole is.
So an electrical dipole is literally a positive charge and a negative charge separated by some amount of distance. And then a monopole is effectively just a single electrical charge, be it plus or minus, right? So magnetic fields only have dipole moments because there is no known magnetic monopole. And all that really means is that the field line leaving the magnetic dipole wraps back around to completely close back. I mean, it's all about electrons moving in some way, shape, or form, right? Anytime an electron moves, it generates a magnetic field. It doesn't matter if that electron were somehow stationary but spinning, it's still moving, so that generates one type of magnetic dipole moment, or if it's orbiting around something, that's the other type.
Yeah, I hear the word dipole moments are around them, and then like we do studying on it, and I'm like, okay, I understand the equation associated with this thing, but what?
So it's easiest to understand by thinking about an electron moving in an orbital path, because an electron physically moving from one point to another is just how we describe current, right? And so whenever we have current flowing, we generate magnetic fields. So if we have an electron flowing in a circular path, the right-hand rule tells us that if our fingers wrap around in the direction of the circular path, our thumb gives us the direction of the dipole moment. So it's just orthogonal to the plane mapped out by the path of the charge carrier.
No, just because, or at least with magnets, all of the electrons pretty much moving in the same direction.
So when you magnetize something, you are lining up its magnetic dipole moments in a particular orientation, right? So you're applying a torque to all of these electrons, because that's what magnetic fields are really good at doing, is applying torques to things and causing those orbits twist in all faces roughly the same direction.
No, it's like, it's just magnetic, like a natural magnet. Is that kind of what's happening innately?
So in a natural magnet, so I'm trying to think of what the technical name for the magnetic domains is, but it doesn't particularly matter. So like in let's say that we have a chunk of iron, right? So that raw iron has these domains in it where all of the magnetic dipole moments are randomly oriented. So it'll have a domain where all of them are, let's say, up, and then another small domain where all of them are to the right, and this, that, and the other. So if we just dig a piece of iron out of the ground, it's not going to be particularly magnetic, like it won't stick to your refrigerator door or anything like that. But when we put it in the presence of an external magnetic field, its dipole moments tend to align with that external dipole magnetic field. And because of the hysteresis properties of that material, which you learned about it in fields already? Yeah, so effectively, if you apply a certain amount of magnetic field, like you'll line up all the dipole moments, but it can only get so good, and that's where you start to hit saturation in your hysteresis curve. When you're coming back down the hysteresis curve, so let's say you turned off the external magnetic field, there is residual magnetization. So that material effectively has some amount of memory because it's stored what its dipole moments are looking like at that instant of time, even with no external energy applied to it. It takes a certain amount of field in the opposite energy to demagnetize that material, and then the loop changes.
That sounds like, very basic, hard drives.
Yeah, that is exactly how like tape hard drive, or, old tapes, media, the spinning disk, hard drive and all that kind of stuff, that is 100% how they work.